Okay, thank you, Renaud, for this nice introduction, and thanks for your first two talks on extreme forms and lattices. Well, and I start with the content of this talk. I want to introduce strongly perfect lattices. And the most important point is here, the red theorem, that strongly perfect lattices are examples of extreme forms. And this notion of strongly perfect lattices has been introduced by Boris Venkov, who gave lecture courses really on this subject in the 90s, in Aachen, in Bordeaux, in Dortmund. And well, so I will show this later. There is a lecture note written by Jacques Martinet about this classes given by Boris Venkov on réseau et design sphérique. It's in French, but for most of you, it should not be such a problem. And so everybody who wants to learn really about strongly perfect lattices is invited to download the lecture notes from the homepage of Jacques Martinet. You don't have to buy a book for this. So this is one point I want to make. Yeah? So I want to give you a method to construct, or probably not really construct, but to construct extreme forms, certain very nice extreme forms. The other purpose is to show that, to give you some examples of lattices. You didn't have really seen examples in the talk by Renaud Coulangeon, probably the hexagonal lattice, the unique extreme form in dimension 2. So examples are root lattices. And here you already see root lattices. Why are these roots? Why? What does it mean, root? It comes from the theory of Lie algebras. So lattices don't live on their own. They live because there are so many connections to other mathematical theories. And here, root lattices have strong connections to Lie algebras, to algebraic groups, to Weil groups, to lots of other things. So the strongly perfect root lattices are exactly these 6 lattices. So there are A1, A2, D4, E6, E7, and E8. So this is one thing I want to show you and how to do it. The other point why these strongly perfect lattices are so interesting is that with their definition, Boris Venkov enabled us to use combinatorial tools to classify them, but also to use representation theory to show that a lattice is lattice is strongly perfect. Namely, when the automorphism group of the lattice is big in a certain sense, then the lattice is strongly perfect. And this is something you know without constructing the lattice. So we can construct local maxima of the density function without constructing the lattices, just from theory, because we know something about the automorphism group. Similar, modular forms. Yeah, we can also use modular forms to show that certain lattices, certain families of lattices are strongly perfect. And this shows, for instance, in dimension 32, that there are more than 10 million extreme forms without constructing them, of course, just from theory. And this is something I like quite a lot. Of course, I cannot go into details here. This would take a full week, yeah, this table of contents, but at least I should define strongly perfect lattices. You should see something about root lattices. And well, this is just one slide, I think, about automorphisms and modular forms each. Okay, let's start with definitions. I'm working in Euclidean space, so I fix the quadratic form. It's always the standard inner product. The lattice is also called L, like in Renaud's talk. The minimum of L is the minimum of the quadratic form on L, or the square length of the vectors, non-zero vectors in L. And the set of minimal vectors I denote by big min of L. This was S of L in the talk by Renaud. So I changed the notations a bit. Okay, this is something you haven't seen, but it will play a role when we talk about dual lattices, about modular forms or dual strongly perfect lattices. With a lattice, you also have the dual lattice. If the lattice is spanned by a basis of Euclidean space, then the dual basis, it's canonically attached to the other basis. The dual basis spans the dual lattice. The dual lattice is just a set of all elements in the Euclidean space having integral inner product with all the lattice vectors. And then you can call a lattice integral if it's contained in its dual. Well, of course, this means that all inner products of the lattice vectors are integers. And I call it even if the square norms of the lattice vectors are even. Even lattices are always integral. Nice exercise. It's because of this factor 2 in the binomial formula. So L plus M, the inner product with itself, is LL plus MM plus 2LM. And if everything is even, then 2LM is even, and so L and M have integral inner products. Okay, even lattices are integral and contained in their dual lattices. But I would really want to define automorphisms. The automorphism group is just a stabilizer in the orthogonal group of the lattice L. If you have already seen some computational group theory, then you know computing a stabilizer, but in an infinite group. And the automorphism group will be always a finite group. That's something I will show. So this is not the point to do an orbit stabilizer algorithm to compute the automorphism group. There are certain automorphisms that are always, that we can always write down. And now I'm coming to the notion of reflections. If I have a non-zero vector in a Euclidean space, then I can always reflect along this vector. This is a reflection sigma index V. It negates the vector and is the identity on the hyperplane that is perpendicular to the vector. Okay, in particular, it's an orthogonal mapping. And this is one possibility to construct some automorphisms of a lattice. If you have an integral lattice, and now if you have an integral lattice, then x comma v is always integral if x and v lie in the lattice. And then this is an integral linear combination of x and v if and only if the norm of v divides 2. And so if the norm, the square length of v is 1 or 2, then this reflection is an automorphism. So root lattices will be even lattices. And in this case, if L is even, then I define the reflection subgroup of the automorphism group of L, just as a span, the subgroup generated by all the reflections along roots or along vectors of norm 2. Okay, so this is all I wanted to define. And these are the notions I will use in the following. So if you already downloaded the talk and have the laptop handy, then this is one slide you can just have open. Okay, so these are the definitions. The first thing I want to show is that the automorphism group of L is always a finite group. So how do you compute the automorphism group? Of course, I say, okay, I always fix the same, I have the standard inner product, and then I have some coordinates for the lattice vectors. And my lattice vectors will be row vectors. That's also a difference to Renaud's talk. So yes, but of course, in the computation, I work with matrices and not, and with matrices, with integral matrices, I would prefer, and not with real numbers. So if you want to compute with a lattice, you choose a basis, the lattice basis, yeah, so that the lattice is really the set of all integral linear combinations of these basis vectors. And then you compute the Gram matrix of B, the matrix of inner products of these lattice vectors. And what are automorphisms? Well, these are all the integral matrices that satisfy the matrix times the Gram matrix times the transposed matrix is equal to the Gram matrix. So in principle, you need to solve such an equation and write down all the matrices. It's of course difficult to do this because you want to have integral solutions of these. Okay, how do you do it to compute the automorphism group? The first observation is that on the diagonal, the Gram matrix has integral entries if you have, well, if you have an integral lattice, but there are real entries and these are always positive numbers and they have a maximum. So that you have n positive numbers and you put the maximum is just this number a. Of course, a good basis would have a small a, because then the set of all lattice vectors having norm smaller than a is smaller, as small as possible. You want to make this as small as possible. It's always a finite set. It's contained in a ball, and it's contained in a discrete set, the lattice, and discrete and compact means finite. That's one way to see it, that this is always a finite set. And the important thing is, whenever I have an automorphism, the images of the basis vectors, they have the same norm as the basis vector itself. In particular, they lie in this finite set. And so we have proven that out of L is finite because this finite set has a cardinality, say big A, and then we only have a to the n possibilities to choose the images of the basis vectors, which are in there. And hence a to the n is the maximum number of such matrices, MB of G, that you can find having, so that, that can be an automorphism. Of course, it's not a good bound. But in principle, this is the algorithm to compute the automorphism group of L. Just look as a subgroup of the symmetric group of this finite set and try to find out which elements of this symmetric group are really automorphisms. And then there are of course conditions. You need to have linear mappings and all these things. But I don't want to go into details, but this is really the point. You compute this finite set and then try to do a backtracking to find which permutations are really automorphisms. So we have seen, at least, it's always a finite subgroup of the orthogonal group. And if you choose a basis of the lattice, then you can get matrices with respect to the lattice basis. And these are, of course, integral matrices because they preserve the lattice. And this is a finite integral matrix group. The last remark shows that the reflection group, well, it's always a normal subgroup of the automorphism group of L, but probably I just skip it because of the time. So let's come to root lattices. What is a root lattice? Well, it's a root lattice if it's spanned by vectors of norm 2. It's an integral lattice. Yeah? So it's just all integral linear combinations of vectors of norm 2. They form a lattice and they form this root lattice. And the lattice should be even. Yeah, okay. Then the set of minimal vectors gets another name because they are roots. R of L is just the set of all vectors of norm 2, the set of roots in L. And yeah, so this was S of L in Voronoi talk, min of L in my talk, and R of L for root lattices, another special name. And we want to classify or to look at indecomposable root lattices. This means that the root lattice is not the direct sum of proper root lattices M and N, the direct orthogonal sum of proper root lattices. Orthogonal sums, yeah, it's a trivial construction of lattices and it will not yield perfect lattices. So yeah, only indecomposable root lattices can be perfect. Okay, the first thing is, if I have an indecomposable root lattice, so it's not the orthogonal sum of proper other root lattices, then the reflection group acts irreducibly on the underlying space. And I want to do a proof, also showing what this means, irreducibly. What does it mean, irreducible? Well, it doesn't fix a subspace other than the full space, that's R to the n, or the zero space. Okay, so if it doesn't act irreducibly, then it fixes a subspace and assume that there is such a subspace. Okay, and then I choose a root that is not contained in U. Yeah, because if it's indecomposable, the lattice is spanned already by the roots, then also the space is spanned by the roots. So not all the roots can be contained in U. And then I look at the reflection, sigma A, and apply it to an element in U. This is a U. Okay, usually it's x minus x comma A divided by A comma A times 2 and then A. But A comma A is 2, so it's just this easy formula. It's U minus U comma A times A. But it's in U for all U in U. And this means, yeah, A was not in U. So this coefficient should be 0. So U comma A should be 0 for all U in U. And this means A is in the perp of U. So any root that is not contained in U is contained in the perp of U. This means R of L is contained in U, union U perp, and this means that L is decomposable. Huh? I can just look at the sublattice spanned by the roots that are in U, call it M, and look at the other sublattice spanned by the roots that are in U perp, call it N, and then I get such a decomposition. That's an important point, because this will show that all root lattices are, all indecomposable root lattices are eutactic, just from the automorphism group. Okay, indecomposable root lattices, what is known? Okay, let's look at this. Indecomposable root lattices, they are classified. I don't want to classify it here. Well, if you want to see a classification, I have the next book, Lattices and Codes by Wolfgang Ebeling, a course partially based on lectures by Friedrich Hirzebruch. It's also already the 3rd edition, but probably there's another one. Lattices and Codes. He gives a nice introduction to lattices and modular forms, but also gives this classification of all indecomposable root lattices, because also he wants to have examples of lattices and codes. And that's easy to read. It's in English, and yeah, so I can recommend this book. Okay, so the root lattices are all classified. The number of roots is written here. Yeah, so if I have a classification, I have a description of this lattice AN. The Dn is just the even sublattice of the integer lattice. Yeah, AN is well, is easily most easily constructed if you look at the perp of the all ones vector in Z to the n plus 1. Here I wrote down the determinant. It means that well, that's the number of elements in this finite abelian group L dual mod L. And here I give this isomorphism type of this abelian group. Okay, the minimum of L is 2, of course, and the minimum of the dual lattice I wrote down here. What you should take from this slide is that the root lattices are all classified. One knows a lot a lot about this root lattices. One knows the number of roots, but there's an explicit description of the minimal vectors. We know the automorphism groups and all these things. And in particular, one thing that is nice, that's an important information is the Coxeter number. This is just the number of roots divided by n. And it's always an integer, if you look here. Huh? Here you see it's the number of roots is a multiple of the dimension, but also here you can divide this by 6, this by 7, and this by 8. So the Coxeter number is always an integer, and it plays a role proving that root lattices are strongly eutactic. Okay, now I come to the key points. This was perfection and eutaxy and Voronoi's main theorem that you have seen in Renaud's talk. Okay, so Renaud defined something that's called Qx, if I have a non-zero vector in the Euclidean space. I define it as pi x. It's a scaled version, yeah? Qx was just x times x transposed, if you look with in column vectors, and for me it's x transpose times x. It's a matrix. And if I divide by the norm of x, then I get a projection, the orthogonal projection onto this one-dimensional space. Okay, so this is the Qx in Renaud's talk up to scale on it. So, and the other thing I want to recall from the talk by Renaud, if I have a symmetric endomorphism, a symmetric n by n matrix, then it defines a quadratic form on R to the n, just mapping alpha to PA of alpha. This is alpha times A times alpha transposed in my notation. It's probably, Renaud just noted it by A applied to alpha with this bracket. And the other thing, this was very, very important, is the inner product on the space of symmetric n by n matrices. It's a Euclidean inner product, just taking the trace of the product. Okay, the trace of the product of the two matrices. If you look here, well, you have this strange factor that was omitted in Renaud's talk, but otherwise you don't get an orthogonal projection. So it's the trace of A times X transpose X. But you know, in the trace, you can just commute matrices. So it's the same as the trace of X times A times X transposed. X times A times X transposed is just evaluation of the polynomial PA at this value X. So PA of X is the inner product of A and QX, well, okay, A and pi X, if you allow the scaling factor. Green is usually what I recall from some other talk. Okay, this is also something I should recall from the talk of Renaud. The lattice L is perfect if these Qx, or equivalently the pi x, they span the space where x runs through all the minimal vectors. They span the space of all symmetric n by n matrices. L is called eutactic. Well, remember, I am always talking about the standard inner product. Yeah? And then it just means that In to the inverse, okay, but the standard inner product is self-inverse, is a positive linear combination of the pi x's. And I call L strongly eutactic if all the eutaxy, these coefficients of eutaxy can be chosen to be equal. Okay, so what is quite easy to see, if I have a perfect lattice, then it should have at least as many minimal vectors as the dimension of this space. The dimension of this space is n times n plus 1 over 2. But pi x is the same as pi minus x. And of course, if x is a minimal vector, then also the negative. And so I should have twice as many minimal vectors. Decomposable lattices can never be perfect because these projections along minimal vectors are isosymmetric endomorphisms of Rm or symmetric endomorphisms of Rn. Well, so, and this will never span the full space of symmetric endomorphisms. So the decomposable lattices are not interesting in Voronoi theory. Well, and the other remark is that eutactic lattices, the minimal vectors span the space. Okay, so the first connection to indecomposable root lattices is that indecomposable root lattices are eutactic, even strongly eutactic. Okay, recall the Coxeter number, the number of roots divided by the dimension. And I claim that if I take the summation x in R of L, x comma alpha squared, this is the same as twice the Coxeter number times alpha comma alpha as a polynomial in alpha. Okay, and for the proof, I only need the automorphism group. I look at this polynomial, the left-hand side here. It's a polynomial in n variables. I map this alpha, if you choose a basis, it's alpha 1 to alpha n, onto this sum, in R. It's an out of L invariant polynomial of homogeneous of degree 2. We have seen that already the reflection subgroup of an indecomposable root lattice is irreducible over the reals. And this means, and this is something that's quite easy in representation theory, that all invariant polynomials of degree 2 are scalar multiples of the quadratic form. And now it's a nice trick. If you know that such a very precise polynomial is a scalar multiple of the quadratic form, then you can just take the derivative to compute that this constant can only be twice the Coxeter number. And this is fairly easy, just applying the Laplace operator and knowing how to derive the quadratic form and the inner product of x with alpha. I don't want to go into details of this proof, but just remember that's very, very easy. You know that this is a constant multiple. Then the constant is uniquely determined just by taking the derivative. Okay, so we know it's a constant, and this is then this constant is 2h. Here it is, the theorem. Okay, but I promised to show that irreducible root lattices are strongly eutactic. Yeah, okay. So strongly eutactic was something with this pi axis. So I want to show that there are eutaxy coefficients, and these are 1 over h. H is the Coxeter numbers. They are all the same, such that this sum is the identity, the inverse of the quadratic form. Okay, let's do it. I compute alpha times pi x times alpha transposed, and you should somehow see that this is almost this x comma alpha squared. Because, okay, pi x was 1 over x times x transposed. Yeah, okay, x times x transposed is 2 because we have roots. And then x transpose times x, that's this qx. Yeah? And I just write it like this. This is just replacing this pi x by definition. But then you see alpha times x transposed is invariant, is a scalar product. X times alpha transpose is a scalar product of x with alpha. The other is with alpha with x, but they are the same. We have a symmetric inner product. So here you have alpha x, come on. And here you have alpha x. And so you have the square of alpha comma x. Okay, and this is something we have computed above here. Yeah? This is h times alpha alpha. And now we replace this alpha comma alpha. It's alpha times alpha transpose, but you can also look at alpha times in times alpha transpose. Yeah? Okay. And so now you can just divide by alpha and alpha transposed, because this is true for all alpha. So on the left-hand side and on the right-hand side, we have a quadratic polynomial in alpha. No? And it's true for all alpha in R to the n. And this means that the sum over the pi x is the same as h times in. And then you divide by h to get this relation. And this is exactly the definition of strong eutaxy. But the only thing we needed is here we have an out of L invariant quadratic form. And this should be a scalar multiple of alpha comma alpha. Whenever we have this, then L is strong eutactic. So we have a group theoretic, a representation theoretic criterion. When the automorphism group is big, real, irreducible, then L is strongly eutactic. Without constructing L, just looking at the group. Okay, so we know indecomposable root lattices are strongly eutactic. And now I want to come to strongly perfect lattices. But let's first come to extreme forms. And this is a theorem proven by Voronoi, that a lattice is extreme if and only if it is perfect and eutactic. And I want to show that all indecomposable root lattices are extreme. Okay, we know indecomposable root lattices are eutactic because they are strongly eutactic. So what's for the perfection? Well, we need to inspect the minimal vectors. And this is a case-by-case discussion. We know about the minimal vectors. For instance, the minimal vectors of the AN lattice, well, you can write them here in n+1 dimensional Euclidean space, just the differences of an orthonormal basis in an n+1 dimensional Euclidean space. These are perpendicular to the sum of all these EI. And so they live in sum of all EI perp. And this is the underlying space where AN lives. Okay, and I want to show by induction that AN is perfect. Then we assume that AN minus 1 is perfect, and we need to show that these projections onto the new vectors here, these PI, EI minus EN plus 1, are linear independent modulo the projections onto the minimal vectors of AN minus 1. Okay, this is a linear algebra task. It's quite easy to show. And then we have the dimension of the space is big enough. This is how one shows that irreducible root lattices are really perfect. And we have seen they are strongly eutactic, and so they are extreme. So we have seen infinitely many examples of extreme forms in this lecture. Okay, they are also strongly perfect. Some of the root lattices are also strongly perfect. And now I come to my main point of the talk, the strong perfection. This is a definition due to Boris Venkov in the 1990s, I think. A lattice is strongly perfect if and only if the minimal vectors form a spherical 5 design. Oops. Now we come to designs. Why this? You will see. Okay, what does it mean, a spherical 5 design? It means that whenever I take a polynomial, homogeneous of degree at most 5, this is the 5 here, 5 design, the strength of the design, then the mean over the minimal vectors is equal to the integral over the sphere where the minimal vectors lie in. Of course, you can scale it. If you scale the lattice, multiply everything by 10, then you also need to scale the sphere here. Otherwise, this doesn't hold anymore. Okay, this is a definition, but of course, that's not how Boris Venkov found the notion of strong perfections. I think the first notion that was around was this strong eutaxy. This is already coined by Quebeman. Strong eutaxy, that's something you really stumble about when you look at root lattices. They are strongly eutactic. And whenever you want to prove that root lattices are extreme forms, you really need to do this, and you will find that they are strongly eutactic. They have the same eutaxy coefficient. And then, yeah, so this is a design condition, because this means that they form a two design, spherical two design. And then it's not so far to come to strong perfection, meaning that they form a spherical four design, and the odd numbers you get for free. Why this? Okay, whenever you have a 4 design, you also have a 5 design. Because if I have a polynomial of degree 5, this is an odd degree, and I replace x by minus x, then p of minus x is just minus p of x. The minimal vectors are closed under multiplication with -1. Yeah? With x, also minus x is a minimal vector. They have the same norm, and they also both lie in the lattice. And so for odd degree homogeneous polynomials, you get the left-hand side is always 0. But also the right-hand side is 0, because also the sphere is closed under taking the negatives. You just divide it into 2 half spheres, and then the integral over the 1 half sphere is the negative of the integral of the other half sphere. And of course, yeah, the integral will be 0. Okay, so odd numbers you can always forget if you look at designs. So yeah, the other equivalent condition is that you only need to look at harmonic polynomials of degree 0, 2, and 4. But of degree 0, well, there are no, these are the constants. But of course, for the constants, for constant polynomial, you get 1 on both sides. And yeah, okay, and degree 2 and 4, you only need to look at the harmonic polynomials, and these are perpendicular to the constants. And this means that here, the integral over the sphere of a harmonic polynomial will be 0. So you don't have to evaluate integrals over spheres of polynomials. You just need to look at harmonic polynomials. This means that the Laplace operator applied to f is 0. And then, this is something that you can easily do by differentiating polynomials. And for these harmonic polynomials, you should get 0 if you do the sum over the minimal vectors. It's also equivalent to say that, we had this for squares, and here just the quadratic form. It's equivalent to say that there is some scalar multiple, some scalar, such that the sum of the force powers of the linear forms given by x is the same as the square of the quadratic form. And this is a representation theoretic condition on the for the automorphism group. You can, because on the left-hand side and also on the right-hand side, there are polynomials of degree 4 invariant under the automorphism. Well, and these are the equations I really want to show you, because these are the equations, if you want to classify lattices, strongly perfect lattices, these are the explicit equations you work with. D4 and D2 It means, yeah, so this sum should be a scalar multiple of the square of the quadratic form. And I showed you, applying the Laplace operator twice, you know which scalar multiple. If it's a scalar multiple, then the C here is necessarily this number. 3 times the number of elements of the minimal vectors times the square of the minimum, m is the minimum of L, times divided by n and n plus 2. And this is something you already have seen. That's a strong eutactic condition. Yeah, the square of the linear forms and summed over x. It's just the quadratic form and up to a scalar multiple. And this is something you can compute applying the Laplace operator. These two equations, they are quite nice. And we have them to classify strongly perfect lattices and to show that strongly perfect lattices are extreme. So I already have commented on this equation D2. This D2 implies that L is strongly eutactic. D2 means, yeah, so this one here is is a scalar multiple of the quadratic form, and which one is quite easy to see. And yeah, if you look at, divide this by m to the other side, the minimum, then this is just alpha pi x times alpha transposed. And this is alpha times in times alpha transposed. So the sum over the pi x is a multiple of in, and this means strong eutacity. Okay, we already have seen it for root lattices, and here again for strongly perfect lattices. And the four design applies perfection. How can you prove this? Well, every symmetric matrices defines a polynomial PA. That's something I recall. And what I want to show is that the pi x really span the full space of symmetric matrices. Well, it's too difficult to compute the dimension and to show that every matrix is a linear combination of the pi x's. It's much easier to show that the perp of U is 0, because then we have some equations. So we want to show that the perp of U is 0. Okay, now we take a symmetric matrix that is perpendicular to all the pi x. This means that the trace of pi x times a, or a scalar multiple of pi x times a, is 0. This is the inner product that we have on the space of symmetric matrices. Again, the trace is commutative in the, you can commute the matrices under the trace. So this is just PA of x. Okay, we know that PA of x is 0 for all x in x. So we also know that 0 is the sum of all the PA of x squared. I can also divide by x to see that this PA is a polynomial of degree 2. So PA squared is a polynomial of degree 4. And 4 design just means that this mean value of the polynomial of degree 4 evaluated at x is the same as the integral over the sphere. Yeah, but this means that PA squared is always positive. Yeah, we have a square. And this is really an inner product. Yeah, this is the inner product of PA with itself on, if you look at polynomials of a fixed degree over the sphere. So if this is 0, then the polynomial is identically 0 on the sphere. And this can't happen. Now I have a homogeneous polynomial that is identical 0 on the sphere. Homogeneous means if I scale a vector, it's the polynomial also scales. And this means that's identically 0 on the full space. And so this means that PA is 0, and so A is 0. And this is really what we wanted to show. It's a very, very easy proof. And I think the proof came probably first before the definition of strong perfection. It was a different proof that Venkov gave, but I think that this is somehow behind this definition of strong perfection. That we can easily show that using some linear algebra, that the pi x really span the full space. Okay, it's red because this is the main result of this talk. Okay, strongly perfect lattices are extreme local maxima of the density function. That's nice, because strongly perfect lattices are not just some local maxima, but you can bound the minimum from below. The minimum of L times the minimum of its dual lattice is always bigger or equal to n plus 2 over 3. And that's a very, very nice proof. I think I show you everything, because here I recall the two definitions of D4 and D2, these equations. And I just take the difference, D4 minus D2. That's something you can do. And so I just wrote it as a factorization. So it's x comma alpha squared times x comma alpha squared minus 1. Now x lies in x, and this is the minimal vectors of L. And I take alpha in the minimal vectors of L dual. The dual lattice only takes integral inner products. So x comma alpha is integer, that's okay. And x comma alpha squared minus 1. Well, if this is an integer, then, well, it could be 0, but then this one is already 0. It could be 1, then this factor is 0, or it's bigger than 2. Now, if it's bigger than 2, then the full product is bigger than 0. Huh? Okay, so here, this product is always non-negative. But if I look at D4 minus D2, I just take the common factor, that's x, m, n, alpha, alpha. Here you have an x, you have one of the minimums. M is the minimum of L. You have this n, and you also have it here, and the alpha, alpha. And what's remaining is 3 times m divided by n plus 2 and multiplied by alpha, alpha. And here there's just this minus 1. Okay, this is positive. This is, of course, non-negative. This is positive. Okay, so we have bigger or equal to 0. And this means that 3 times m times alpha, alpha divided by n plus 1 is bigger or equal to 1. M is the minimum of L. Alpha, alpha is the minimum of the dual. And then you should just bring the 3 divided by n plus 1 to the other side of the inequality to get this inequality. Minimum of L times the minimum of L dual is bigger or equal to n plus 2 over 3. We will use this twice at least. One, to classify all strongly perfect root lattices, and this is the next slide. Okay, we only have A1, A2, D4, E6, E7, and E8 as strongly perfect root lattices. So the first thing is, well, there are no other strongly perfect root lattices. Of course, strongly perfect root lattices are perfect and hence indecomposable. So we only need to look at indecomposable root lattices and compute the minimum of L times the minimum of the dual. To see, well, if whenever I have this bigger or equal to n plus 2 over 3, then it's necessarily one of these 6 lattices. is probably boring. But yeah, so we use this condition, compute the minimum times the minimum of the dual. The minimum of L is of course 2. And yeah, so we see that we only have these possibilities. Okay. But now we need to show that these are really strongly perfect. These 6 lattices are strongly perfect. Okay. So I think it would be enough to show that this one here is a scalar multiple of alpha alpha squared. Or that this polynomial P is identically 0 on the full space R to the n. Well, it would be possible to compute with polynomials because we only have these explicit lattices. But nevertheless, this is much harder than evaluating a number. And I want to show you a nice trick that boils down from this polynomial. You can really say, okay, I introduce an inner product again on the space of polynomials so that I can reduce computing a number. And this is a nice inner product. It's an ON invariant inner product on the space of all polynomials that are homogeneous of degree T. And what do? I take 2 of these polynomials of the same degree. I take one of them and replace the variables by the derivatives with respect to these variables. And then I get a differential operator and apply this to this polynomial f to get a number. And it's not so difficult to see, well, to prove that this is really a positive definite symmetric inner product. The easiest way is to do this for monomials. Yeah? If I have a monomial here and a monomial there, well, if they are different, this will be 0 because then you do a derivative with respect to some variable to a higher power than it appears in f. Yeah, for monomials, the monomials form an orthogonal basis, and then you need to compute the derivative of a monomial with respect to itself. It's always a positive number. Okay. It's also easy to show that, yeah, okay, so when G is just the quadratic form, then it's this inner product is applying the Laplace operator to f. And if G is a power of the linear form, then f comma G is just f of x. Yeah, this is something you should compute in advance to show that if you look at this polynomial, of which we want to show that this is 0, this polynomial, evaluated the inner product with itself, can be computed like this. This means I can show that the lattice is strongly perfect just by summing up the 4th powers of the inner products of the minimal vectors. And this should be equal to this constant. It's always small or equal because the norm is always a non-negative number, but it should be 0, so it should be really equal to this, as large as possible. And this is something you can do for these 6 root lattices. It's very easy. And then you do it with computer, of course, and show that these are strongly perfect. So strongly perfect lattices are classified up to dimension 16, I say. Well, up to dimension 12, all the strongly perfect lattices are classified. In higher dimensions, it's quite complicated to classify all the strongly perfect lattices. And there we assumed that also the dual lattice is strongly perfect. All these lattices in smaller dimensions, they satisfy that also the dual lattice is strongly perfect automatically. But here we don't know whether there are other strongly perfect lattices so that the dual is not strongly perfect. I don't give names because I'm short in time. So there are up to dimension 24. These are the lattices that are already in the lecture notes by Boris Venkov in this blue book. And Also, the lattices here in this table are almost all included in the table here of this lecture notes, except for H16. And this is something we found when we, as a sandwich Barnes-Wall lattice, when we classified these 16-dimensional strongly perfect lattices together with Shi-Huang Hu, who was a Chinese postdoc from an AVH, Alexander von Humboldt fellow in Aachen, and he is now professor in China. And yeah, so he found a new lattice, and this was the first new strongly perfect lattice after the lecture by Boris Venkov. So all the others were already known to him. And probably for dimension 21, that's the only lattice known, strongly perfect lattice known, that is not dual strongly perfect. Okay, this is the classification. The methods are combinatorics. Yeah, you just exclude possibilities of kissing numbers and all these things. And I cannot go into details because I want to show you the last two slides where I apply representation theory and modular forms to show that certain lattices are strongly perfect. Representation theory, well, we have seen if all out of L invariant homogeneous polynomials of degree 2 are multiples of the quadratic form, then the lattice is strongly eutactic. And if you also have a condition of the degree 4, then the lattice is strongly perfect. And of course, the lattice of the automorphism group of the dual lattice is the same as the automorphism group of the lattice. So we have a dual strongly perfect lattice. And this is my favorite example because you just look into the atlas, the atlas of group representations, and you find that there is a sporadic simple Thompson group having a 248-dimensional representation. It's the smallest degree. You can realize the Thompson group. It is a rational representation, and we have a finite group. So I know that rho of G fixes a lattice in this space. And modular representation theory shows that this is a unique lattice up to multiples. So it's an even unimodular lattice. Now I do character calculations to check these two things, that you only have a one-dimensional space of homogeneous invariants of degree 2, 4, and also 6, but you don't need 6. In particular, we have this condition for 1 and 2, so L is strongly perfect by this, the theorem before. And from this, we know that the minimum of L is at least 10. Without constructing the lattice, I just can look at the character table of the Thompson group for this, probably the decomposition numbers, to get this. And then, of course, you can construct the lattice and you find a vector of norm 12, but still unknown whether the lattice has minimum 10 or 12. There's one thing, how you can show that you find dual strongly perfect lattices, and I already mentioned the sandwich Barnes-Wall lattice found by Shi-Huang Hu. And yeah, all these lattices, it's an infinite series. The Barnes-Wall lattices and sandwich Barnes-Wall lattices are dual strongly perfect lattices because their automorphism group is big. Okay, last slide, a criterion for modular forms. And I think I go through everything. If I have an even unimodular lattice, then I know the dimension is a multiple of 8, and I write it as a multiple of 24 plus some remainder. This is then 8, 16, or 0, 8, or 16. And then I know that the minimum, by the theory of modular forms, the minimum of L is at most 2a plus 2. This is something already that was known to Siegel, and he really studied modular forms to show this, that even unimodular lattices have an upper bounded minimum. And if a lattice reaches this bound, then L is called extremal. Siegel already showed that there are only finitely many extremal lattices, but nevertheless, there are many, finitely many, but many. For instance, in dimension 32, there are more than 10 million extremal lattices. And now the theory of modular forms helps to show that extremal even unimodular lattices are strongly perfect. And so whatever we construct, we have a large minimum, or whether we note, we can just count the number of extremal lattices. This was done by Oliver King, by a nice counting formula. So you have so many local maxima of the density function, strongly perfect lattices. Well, and to end the talk, I just summarize what we did. We have shown, and that's the main result, strongly perfect lattices are extremes. And the notion of strongly perfect lattices opens us up to the use of other theories, namely, for instance, combinatorics and designs to classify strongly perfect lattices. We can show that root lattices are strongly perfect. Some of the root lattices are strongly perfect. We can use automorphism groups and modular forms to show that lattices are strongly perfect, respectively, dually strongly perfect. And this is the end of my talk. Thanks for your attention.